Hello, everyone. Dr. White here with our second screencast on the binomial distribution. We are now going to talk about how to find probabilities for binomial random variables with the function pbinomGC. Let's give ourselves a binomial situation and a binomial random variable to work with. Let's say that you are faced with a multiple choice test that has 20 questions on it. Each question has 4 choices, but only one is correct. So there's really 2 outcomes for each question, correct and not correct. And let's say you just don't know anything, so you guess on each question. Well then, 4 outcomes, you're going to have a 1 in 4 chance of success, 3 in 4 chance of failure on each question. And let's say that to pass, you have to get at least 8 questions correct, 8 or more correct out of 20. What's the chance that you fail, that you don't pass? Well, we've analyzed it out that the number of questions that you get correct is a binomial random variable. It's got 20 trials and chance of success 1/4 or 0.25. We're looking for the probability that you fail, which is getting 7 or less. So we're looking for the probability that x is less than or equal to 7. So there's an R function that comes in the TigerStats package called pbinomGC. P for probability, binom for the binomial distribution, GC for graphical calculator, if you like. It works a lot like pnormGC. First input is your boundary number for the probability, 7. Then you need to talk about how many trials are in your binomial random variable, and that's done with the size parameter here. You also need to talk about the probability of success, and that's done with the prob parameter. So you'll need 2 inputs like that. They don't have to come together, but they got to come somewhere. You also got to say region is below, and that cues R into the fact that you want the probability of 7 or less than or equal to 7. Graph is true is going to help you to understand the situation better by giving you a graph of a probability histogram for this binomial random variable. Let's give it a try over in RStudio. So we head to our console, and I'm going to make it big for a moment so you can see better. Paste in the code, run it, and we do get a graph over in the plots window, and we get in the console here where I'm waving my mouse the probability. The chance of failing is apparently 0.898, about 89.8%, nearly 90% chance of failing. So, the picture that you see over in the plot window, the rectangles are represent a lot of the possible values of the binomial random variable. There's actually 21 possible values, all the way from 0, 1, 2, 3, up to 20. That's 21 values. And the height of each rectangle gives the probability. A better look at it might be back in the slides on the next page. Make this a bit smaller. So, for example, the chance of getting exactly 7 right would be the height of this shaded rectangle here over the 7. That's a little bit more than 0.10, a little bit more than a 10% of getting exactly chance of getting exactly 7. The sum of all the heights comes up to the 0.898, the roughly 90%. Not all 21 rectangles appear on the graph because some of them had heights that were so small that R decided that it wasn't worth trying to graph them. So the actual rectangles only go up to the 1/8, 9, 10, 11, 12, and there's 1/13, and that's the last one to even try to think about. As for other rectangles, 6, 5, 4, 3, 2, 1, 0, it did go back to the smallest possible value. There is a teeny chance of getting 0 right. But the sum of the heights is that probability that you see down in the console where I'm waving my mouse. Let's try another one with the same situation. You're on that 20-question test. What's the chance that you get more than 5 questions right? More than 5. Same approach with pbinomGC. You put in your boundary number as your first input, and then you specify the other parameters, except you're going to say region is above. That's for the more than 5. If you were to run this in RStudio, in the plots window, you'd get this graph here. And you would get this probability down in the console. The chance of getting more than 5 right is about 38%. Notice that when you put your boundary number as 5 and your region is, quote, above in the R function, then you start at the next higher number, 6. That's really important. When you're working with less than or equal to probabilities, when you're saying region is below, then this function will include the boundary number. Like in our first example, it included the boundary number 7 in the heights that get summed up. But in our second example, where the boundary number was a 5 and region is above, the 5 rectangle did not get included in the heights that are summed up. That's just something you'll have to remember about how pbinomGC works. Here's another question. What's the chance that you get from 6 to 8 questions correct? So 6, 7, or 8. With pbinomGC, similar to how you would use pnormGC, you need to stick your two boundary numbers together with the C function as your first input. Again, you'll specify your binomial random variable with the size and its prob, and somewhere you have to say region equals between. And you will get, as your answer, the sum of the heights of the 3 rectangles corresponding to the outcome 6, 7, or 8. So when you do region is between, your boundary numbers are included in what gets added up. What's the chance you get exactly 7 questions correct? Is there a way of answering that question? Yes, there is, if you use region is between and a little trick. pbinomGC. Throw in your 2 boundary numbers, but they're both 7 with region is between. So you're asking yourself, what's the chance that I get from 7 to 7 questions correct? Run this, and you'll only be adding up the height of the 7 rectangle. The height of that rectangle was about 0.112, and that's the chance of getting exactly 7 correct. So binomial random variable is one of those discrete random variables like the ones we first learned about in Chapter 3. For a discrete random variable, the probability that it equals a particular value, like the probability that you get 7 correct, can easily be bigger than 0. For continuous random variables like the normal random variable, the probability of being exactly one number is always 0. Here's another example. Suppose that Buzz, our dolphin, is just a guesser, no communication with Doris. What's the chance that he pushed the correct button 15 or more times in his 16 tries in Dr. Bastian's experiment? Well, let's see. Let's set up a random variable to model the situation. Let's let capital Z be the number that he would get correct in 16 tries. That capital Z is a binomial random variable. There are 16 trials. Every time he has to make a choice between the buttons as a trial. There are two outcomes, success and failure. He pushes the right button, he does not. There's the same chance on each trial, his chance of success, and if he's just a random guesser, that chance is 0.5. All right, so we need to find the probability that that random variable Z is at least 15. Here is a typo in the slides. I'll fix them by the time you get to work with them. That should say we want the probability that Z is bigger than or equal to 15. How do we do it? We head to pbinomGC, and we know that we need to be adding up the chances for 15 and 16 together. So we work with the boundary number 14. We're going to use region as above, and so that'll catch us the 15 and the 16. So if we run this code, we get these results here. The graph is not quite able to show you a rectangle over 16 because that rectangle is so short, it didn't think it was worth showing. The last one it shows is a rectangle at 15. But it shows here in the console where it added up the height of the 15 rectangle and the 16 rectangle. Together they added up to about 0.000259. A very, very small chance indeed. In fact, in the title for the graph, where it says the shaded area, which is this sum down here, it just rounded it down to 0 because the chance was so very, very small. Here's another example. Say you toss a fair coin 100 times. What's the chance of getting between 45 and 55 heads, including the 45 and 55? Well, let's let X be the number of heads. We want the probability that X is bigger than or equal to the 45, but less than or equal to the 55. Well, we know how to handle those questions now. We just stick our two boundary numbers together with the C and say we want region is between. We do need to specify the binomial random variable. It's 100 trials, chance of success 0.5 each time because it's a fair coin. Off we go. And the probability is about 72.87%. That's the sum of the heights of all of these rectangles that you see shaded in here. Here's a little bit more practice. Suppose that Buzz is better than a random guesser, but maybe not much better. Suppose he can get it right only 70% of the time when Doris is trying to communicate with him. Then what would be the chance that he gets it right 15 or more times in those 16 tries? Think about this one for a minute. And then when you're ready, move on to the next page, see how you did. Well, once again, it's pbinomGC with the bound set at 14 and region is above. It's still 16 trials, but now we're assuming the probability of success on each trial is 0.7. What do we get? Now the height of the 15 and the 16 rectangles are both big enough that R sees fit to try to draw both of them. And the sum of those two heights is a good bit more than it was last time, but it's still kind of small. It's about 0.026, about 2.6% chance. So, if Buzz was only a 70% guesser, these results are still pretty unlikely to happen. I think that this 15 out of 16 that he got right is actually fairly strong evidence that he's even better than a 70% guesser, that his communication skills with Doris are better than 70% type of work. Another little piece of practice. If you flip a fair coin 100 times, what's the chance of getting exactly 50 heads? Could you write an R function with pbinomGC that gives you this probability? Here's my solution, pbinomGC, and we're asking for the probability of getting from 50 to 50 heads. See, the region is between. We need to specify the number of trials, and it's a fair coin chance of success is 0.5. Graph is true is not necessary for the numerical answer, but it's always nice to see until you're real familiar with how the distributions for binomial random variables look. Here's the way it would be in our studio. And so the height of the rectangle over 50 is the probability of getting exactly 50 heads in 100 tosses, exactly what you expect. And what is it? Just a little bit under 8%, about 0.0795, just about 8% chance of getting exactly the number of heads you would expect in 100 tosses of a fair coin. Next time we get together, we'll look at the concepts of expected value and standard deviation for binomial random variables. See you soon.